Welcome to the lecture on Introduction to Phase Diagrams. So, while discussing the welding metallurgy course, we very much need to know about the phase diagrams. Now, I hope that you must have some introductory knowledge about the phase diagrams in your initial courses related to material science and engineering or physical metallurgy. So, we will have an overview about the phase diagrams, and in the subsequent lectures we will also discuss about the phase diagram of ferrous system, especially the iron carbon system, as well as some of the important non-ferrous system also. So, coming to the introduction about the phase diagrams, as we know, the phase diagrams are the maps that give the relationship between phases in equilibrium in a system as a function of temperature, pressure and composition. So, what we expect from phase diagram, what informations do we expect? Basically, we are in need of engineering alloys. We know that in most of the cases the pure metals or pure elements are less significance, having less significance as far as the engineering use is concerned. So, what we do is we normally make alloys. We have to add certain element to the parent atom element, and then we have to see that how it will behave, how they are going to behave when they are combined, and how there is strengthening effect or which kind of reactions take place. So, all that basically as a function of temperature, pressure and composition. So, with the change in composition of one element or with the variation of temperature and pressure, what what kind of phases we are going to get in the equilibrium condition. So, basically phase diagrams depict about all these things. Coming to the definitions of the different terms like a phase. So, phase is defined as the physically distinct, chemically homogeneous and mechanically separable regions of a system. So, that is the definition of a phase, and if we talk about the gaseous state or liquid state or solid state, that is what the different states of matter is. When we talk about the gaseous phase, so since there is mixing at the atomic level, so we call it as a single phase. Similarly, if you have a liquid solution, in that case we also call it as a single phase. Now, many a times so that is what we have, that is gaseous, liquid and the solid, they are forming the separate phases. You have also independent chemical species. So, we will talk about components. So, what is component? So, the independent chemical species that comprise the system are the components of a system. So, that is what is the definition for a component, and it may be elements, ions or the compounds. So, basically there is a well known rule given by the Gibbs, and he has given the rule like F equal to C minus P plus 2. So, that is the degree of freedom is defined as F. And so F equal to C. So, the number of components minus P. So, that is number of phases in the system and plus 2. But we will see that how that changes, because when we are dealing with these elements, what happens that many a times with change in temperature, we will see that how at one point you will see that there are many phases in equilibrium. So, and if you change the parameters, like you have the external variables like pressure or temperature or composition, in that case how these change in phases are incorporated, that gets reflected from the phase diagrams. So, what we see that normally you have the variable of a system, you have normally two external parameters, that is temperature and pressure. Now, if C is the number of component in the system, then the number of variables which are required to specify completely the composition of a phase, that is equal to C minus 1. So, for if there are p phases in the system, then in that case that will be p into C minus 1. C minus 1 means that if you know the C minus 1 components, then certainly you know the last component. So, that is why the number of variables which are required to specify completely the composition of a phase, that will be C minus 1. And for p phases, you will have p into C minus 1, and if you take the other two external parameters, that is temperature and pressure, then it becomes p into C minus 1 plus 2. Now, degree of freedom, that is defined as f. So, it is the independent variable among them, and this degree of freedom f, it cannot be more than this total number of variables, that is p into C minus 1 plus 2. Now, according to Gibbs rule, basically f is so Gibbs has given this f as C minus p plus 2, and here you get this f as p into C minus 1 plus 2. So, basically this degree of freedom in that case, so this cannot be more than total number of variables. So, basically C minus p plus 2, this cannot be more than p into C minus 1 plus 2. So, what we can make out from this, that if there is only one phase present, that is p is equal to 1, in that case what you see that so degree of so in that case degree of freedom is equal to the total variable. So, in that case degree of freedom here, it will be C minus 1 plus C plus 1, and in this case also if p is 1, so it will be C minus 1 plus 2, so C plus 1. So, degree of freedom will be equal to the total number of variables, and as you increase the number of variables, so number of phases. So, in that case if you increase that in the if these number of phases, in that you must have, you will see that there is an upper limit to the number of phases that can exist in the equilibrium. So, basically when you will analyze these equations, you will see that how in the multi-component system, we have single component system or multi-component system, then in that case using this formula, basically you can see that at any condition, at any temperature or pressure, what will be the degree of freedom. So, basically how you can change either you can change pressure, or you can change temperature, or you can change nothing of them, because in that case the conditions will change. So, that is basically being depicted by these phase diagrams. So, what we will see next will be if you look at this. So, what we have got from here. So, if you try to see that if you try to analyze, if you see that if your number of phases is suppose 1, in that case your total number of variables, so total variable, that is C p into C minus 1 plus 2. So, you will have 3, and if you have the degree of freedom, so you will see that degree of freedom value will be 3. Now, if you go for the number of phases as 2, so it will be so number of phase becomes now 2 here, and in that case your this one for a 2 component system, it will be 2 into 2 minus 1 plus 2. So, it will be 2 plus 2, that is 4, and for a 2 component system if you take 2 minus 2 plus 2. So, it will be 2. So, normally for 3 phases you will have the total variables is 5 and your degree of freedom becomes 1, and similarly you will have for the 4 phases you will have 6 is the total number of variable and the degree of freedom becomes 0. So, that is how you can see that how many phases can be there, and at some point you will have the degree of freedom as becoming 0. So, we will see that how you analyze the single component system or the multi component system, and how you can discuss about the different traits of these phase diagrams. So, coming to the single component system, now in this there is no compositional variable, and this is basically the pressure temperature diagram for the single component system of iron, and what you see that you have different phases, that is alpha, epsilon, gamma, delta, and all that is shown in such cases. And now in the case of single component system, you can see the different points, and you can find that what will be the degree of freedom at different points. So, if you talk about, so what you see is here this is for the iron, and this is very clear that you have these are the solid phases, and then you have liquid phase here, and then you have gaseous phase at the top. So, when you are in this region, in that case P is 1 and this is single component system. So, if you go to the single component system and when your phase is 1, so degree of freedom will be C minus P plus 2. So, C is also 1 and P is also 1. So, in that case you will have F as 2. It means your degree of freedom is 2. So, basically you can independently vary as long as you are in that single phase region, that is in this region or this region or this region or this region. So, you can basically vary either pressure or the temperature independently, and you do not have you will be in that phase itself. Now, if you come to when your 2 phases are in equilibrium, suppose, and that is normally along a boundary, suppose solid and liquid phase is there on that. So, now in this case you will have 2 phases in equilibrium. So, your P will be 2. Now, F will be C minus P plus 2, C is 1 and P is 2. So, 1 minus 2 plus 2. So, your degree of freedom becomes only 1. Now, that means that if you are changing the you can independently change the temperature, but then the pressure will automatically change, so that you are still in that phase, that is your 2 phase region, that is normally along the boundaries. Now, if so, in that case degree of freedom becomes 1. Now, if you talk about 3 phase equilibrium, so 3 phase equilibrium suppose it is at this point, suppose say. Now, in that case your phase is 3. So, C minus P plus 2. So, P is 3, C is 1, and so 1 plus 2 minus 3. So, in that case it becomes basically F is 0. It means your degree of freedom is 0. So, you if either of the these parameters, if you change either temperature or pressure, in that case you are basically going into the different phase regions. So, you will not be at that point. So, normally that is indicated by a point. So, that is 3 phase region. So, this is about the single component system. Now, if you come to a 2 component system, now in this case basically you will have 3 components which are to be looked into simultaneously. One will be temperature, another is pressure, and the third is composition. Now, that can be seen only on the 3-dimensional graph. So, what we do normally is that we ignore the pressure, we take only temperature and composition. So, basically the Gibbs phase rule, that is F equal to C minus P plus 2. So, in that case that plus 2 will be replaced with plus 1, because we are ignoring the pressure, because pressure does not pressure is seen to not do much of the changes. So, ultimately your for two component system, the phase diagram looks like this. So, F equal to C minus P plus 1. Now, what we see is that normally we can go for a phase diagram of one system where there is complete liquid and solid solubility. So, in that case this is how the phase diagram looks like. So, what we will see that what we are seeing here, that in this case you have this as the liquidus line and this is the solidus line. This is the liquid and this is the solid. So, normally this is typically for that type of phase diagram where the two materials, two components have the solid as well as the liquid complete solubility in them. Now, what is clear from this, you can see that when you are decreasing the temperature from this point, at this point the whole domain is liquid. Now, when you come to the this zone, this is the liquidus line and this is the solidus line. So, the solidus line is separating that solid part with the liquid plus solid zone, and the liquidus line is separating the liquid part with the liquid plus solid zone. So, when it is coming below this, the temperature is coming below this point, in that case the solid will crystallize out, and so what we see is that apart from liquid you have also crystallized solid phases. So, and then you have liquid also, and once the temperature reaches below this solidus line, in that case it completely becomes solid state. Now, what we need to know in this case is that you can see that you have two components. One component has the melting temperature at this point, another component has melting temperature at this point, and as this component percentage is increasing, you can see that its liquidus temperature will be going on changing. Now, in this case we need to know a few things. One is the when we are coming to different points, then the solid which will crystallize, and now this solid will have what composition, and also what will be its fractional part that is formed. So, basically this is known as the tie line, and this tie line is basically talking about the composition. So, the tie line will tell you what will be the composition of the liquid and what will be the composition of the solid. So, based on the tie line, so tie line is meeting here, and at this point liquidus point here and the solidus point here. So, depending upon the tie line touching, your liquid and the solid compositions will be. So, that is what you see. If you have the melt of composition C naught, when it reaches to this point, at this point this tie line is touching the liquidus line at this point. So, corresponding to this point, this is the composition of the liquid. So, at this point you have liquid as well as the solid zone. Now, the liquid zone will have the composition Cl and the solid formed will have the composition Cs, and accordingly when you are coming at this point, it is completely solidified, it will have the composition of C naught. So, the tie line will tell you the composition of the phases. Now, another thing is that what will be the amount of solid formed at a particular temperature. So, that is being calculated with the help of lever rule. Now, the lever rule tells that if you have this point you take as the fulcrum of the lever. So, the fraction this upon whole will be the part of the solid, and the fraction this upon the whole will be telling you about the part of the liquid which is there. So, basically the line, it is touching the liquidous line. So, this part, this fraction will be the fraction of the solid formed, and this fraction will be equal to the fraction of the liquid. So, that these are the two things which we know from these phase diagrams. The tie line and the lever rule, these two principles are used to find the composition as well as the amount of the solid or liquid phases which are there. So, that is formed. Now, in this case also we can apply this Gibbs phase rule to find the degree of freedom, and if you look at the region, that is if you take the single phase region, that is either solid or liquid, in that case that is if you put component is 2. So, 2 minus 1 plus 1. So, that will be degree of freedom will be 2. So, you can independently vary either pressure. So, you will have 3 variables here, composition of so temperature, composition of phase 1 and composition of phase 2. So, you can vary any of the 2 independently so that it is there. Whereas, if you go to the 2 phase region, again in the 2 phase region basically you will have 2 minus 2 plus 1. So, there will be only once if you vary 1. So, one of the composition will be changed. So, it is in the same way it can be interpreted as we have seen in the case of binary system. Now, in this case of complete solubility in the binary system, you do not see a point where the degree of freedom is 0. So, that is what is seen. Now, when we talk about these binary systems, now in such cases what we see that we see many a times the invariant reactions, and so what happens that if you look at the phase diagrams, these are the different invariant reactions which are taking place at a particular temperature, and you have the different invariant reactions like eutectic, eutectroid, peritectic, peritectroid, monotectic, monotectroid and syntactic. So, mostly you will have the first 5 which you will normally be looking at. Now, in this case you will have the transformation from one phase to other. So, liquid will be converting to alpha plus beta, that is in the case of this you will see at many places you will have the eutectic reaction taking place. The liquid is there and it will be solidifying at a particular temperature, and it will make mixture of 2 solid phases alpha and beta. So, normally what you see is in the case of iron carbon system it is at about 1137 degrees centigrade or 1140 degrees centigrade. In that case the liquid is basically, so if you look at, so we will deal with the iron carbon system, and what we will see. So, now in this case so this way so this is 1137 degrees centigrade. Now, in this case here this is at 4.3% of carbon. So, here basically you will have the austenite plus cementite, these 2 mixtures. So, in this side you will have gamma and this side you will have Fe3C. So, that will be formed, and you will have this side as the liquid. So, that is your eutectic reaction, and in many cases in many systems you will come across. So, while cooling, the liquid will be converting to 2 solid mixtures liquid is converting to alpha plus beta. Similarly, when you heat, the alpha plus beta will be heated, and ultimately at a particular temperature your liquid will be formed. Similarly, in the case of eutectoid reaction, you will have alpha converting to beta plus gamma, you have a solid phase, and this when you are cooling, so it is giving you the beta plus gamma phase. So, this is happening in the case of iron carbon system also, and in this case the austenite while being cooling, it will lead to the ferrite plus cementite. So, that is how you have these eutectoid reaction taking place. Apart from that, you have peritectic reaction where the liquid plus alpha. So, that upon cooling will so liquid plus one solid phase will give you another solid phase, and while if you heat, the solid phase will be converting to one liquid plus one solid phase. So, that is your peritectic reaction. Similarly, in peritectoid reaction, you will have two solid phases, and that will be once you cool, in that case it will be giving you another solid phase, and reversibly it will be going on for the while you heat it. So, accordingly, as you see these you must have the understanding about these things, that when you are cooling, so in this case at this point these reactions take place, and you are getting liquid to alpha plus beta, alpha to beta plus gamma. So, alpha plus liquid to beta, similarly alpha plus beta to gamma, alpha plus, so liquid will be to alpha plus another liquid, alpha 1 is alpha 2 plus beta, and similarly liquid 1 plus liquid 2 will be on cooling will be making you the alpha. So, these are the different invariant reactions, and they will be we will be facing these invariant reactions as we discuss the different types of the phase diagrams, either be it for the ferrous system or the non-ferrous system. Now, you will also you may also come across certain type of phase diagram when the solid solubility is limited. In that case, and also the melting point of the components, they are not vastly different. In that case, a eutectic type of phase diagram will be obtained, and that will be. So, if you can have the typical example which you can see will be basically the lead tin phase diagram, and what you see in this case the phase diagram will be like this. So, what you see here now in this case you will have so this is type of phase diagram which is there for the lead tin. So, you will have PB and SN. Now, in this case what you see, this is the example of the so this point what you see. So, you will have this is the alpha phase and this is your beta phase. So, what you see is your this point. So, this is your liquid, and this is something like 327 degrees centigrade, and you will have this case is this is 232 degrees centigrade. Now, in this case what you see is this portion will be liquid plus alpha, and similarly this will be liquid plus beta. Now, in such systems, and here it will be alpha plus beta. Now, this point as we discussed, this point will be your eutectic point, because this liquid composition when it comes at this point. So, after this point when it solidifies, it will make you the alpha plus beta. Now, in these cases you have a liquidus line. So, liquidus line will be the line between the liquid and the liquid plus alpha zone. So, your this line, that is boundary between L and L plus alpha. So, boundary between L and L plus alpha. So, that will be the liquidus 1. Similarly, liquid S2 will be boundary between L and alpha L plus beta. So, that will be your liquid S2. Similarly, you will have solid S line, and solid S line will be basically solid S1 and solid S2. Now, solid S line is normally between alpha and L plus alpha. So, you will have alpha and L plus alpha, similarly beta and L plus beta, that will be your solid S line. So, this is your liquid S line, this is your solid S line. Apart from that, you have also solvus lines. So, you will have liquid S line, you will have solid S line, and also you have solvus line, and solvus line is basically so solvus line is basically boundary between alpha and alpha plus beta. So, these lines alpha and alpha plus beta or beta and alpha plus beta. So, these lines are known as the solvus lines. So, normally you must know that in such cases what these lines are known as. So, these will be your liquidus lines, L and L plus alpha. Similarly, L and L plus beta you will have liquidus lines. Similarly, you will have the alpha solid phase and L plus alpha that line. So, that will be alpha and L plus alpha will be your solidus line. Here also you have solidus line. And then if you talk about the alpha and alpha plus beta zone or beta and beta alpha plus beta zone, in that case these lines we will be talking about the solvus lines. So, these are some of the characteristics of the phase diagrams, and we will be discussing about the phase diagrams of ferrous system as well as non-ferrous system, because we need to have some overview or you must be able to refresh what we have studied in our earlier years. And then this basically knowledge will be utilized when we talk about other welding metallurgical considerations or points when we go and study the different phenomena. So, that is about the phase diagram, and we will further read about, we will further study about or interact about these phase diagrams of ferrous as well as non-ferrous systems in our subsequent lectures. Thank you very much.